Hello, thank you all for coming to this session. I'm Victor Cuevas. I come from the Barcelona Supercomputing Center. And today I will talk with you about our work in benchmarking cloud-based data analytics systems, in particular Databricks, as well as EMR Presto and EMR Spark. First, a brief introduction to the place in which this research occurred. First, the BSc is an academic research institution financed by the Spanish and Catalonian governments. We work, a strong point is high-performance computing, given that we have a supercomputer ranked about 29th in the top 500. However, there is also research related to other broader aspects of computer science, like in this case. Now, also, we collaborate in, European research projects, but also with industry in projects. Now, in our case, we collaborated with Databricks to benchmark these cloud-based analytic systems. In particular, we opted to use the TPC-DS benchmark, which of course is produced by the Transaction Performance Council. However, I should point out that the results I will show today do not correspond to official results of the benchmark in accordance to the regulations and the guidelines of the TPC. Also, I should mention that Databricks generally provided us with an account, as well as the credits that enable us to run these experiments. The goal is, of course, to create an independent evaluation of these cloud-based data analytics systems in order to then make it public and make available to the public to decide which is an adequate option for their needs. Now, the context in which this work takes place, of course, we all know that data analytics are extremely important for businesses and organizations. The question then is, what is the most cost-effective, the most flexible, and adequate manner to incorporate the big data analytics? And the current trend, emerged in the recent years, is, of course, use cloud-based systems. This is due to the fact that, of course, you have at your disposal large amounts of computational resources available fully on demand. And also, in this manner, you get a platform running already with sophisticated systems, most cases based on open source, like in the case of the three systems I will talk about today. And also, I clarify that whenever I'm referring to data analytics, I'm focusing concretely on SQL. Of course, this doesn't represent the entirety of this broad field of data analytics, but still is very much relevant for several types of organizations and multiple tasks. And of course, it is important then to define what is an efficient option to evaluate SQL in the large scale via the cloud. And that is the purpose of this work. Now, the systems under test. First, we have Databricks, the unified analytics platform. Of course, it's based on the Apache Spark technology. But in this case, it incorporates the Databricks optimized runtime and also offers a unified environment in which you have Azure availability, for instance, notebooks, in which you can, data scientists, for example, can work interactively to define algorithms and data analysis pipelines. But also, you can define jobs to run in a cost-effective manner sophisticated data analytics pipelines in a more cost-efficient manner, as you will do in our systems. And of course, you can access it via JDBC or either this conventional Spark Scala API. I will not discuss in depth all these features. For instance, Delta storage, and we see the now Spark on ACID. That is not considered, for instance, in this work. Also, we consider two AWS EMR systems. First, Presto. Of course, Presto was originally developed by Facebook in order to query large amount of data of different types. Concretely, for instance, you can have data on HDFS, but also on a relational database, let's say Postgres, and also on NoSQL databases. And you can access it via JDBC and also has a command line interface. Its model is prioritizes processing in memory in a pipeline highly parallel manner. And finally, EMR Spark, also on AWS, which is of course based on conventional open source Apache Spark. So in terms of the presentation, first I will briefly introduce the TPC-DS benchmark. Then I will clarify the configurations in terms of both hardware and software that we employed in these experiments, followed by also a brief description of the infrastructure we had to develop in order to be able to run these experiments. And of course, the core of the talk is, of course, the benchmark results and an analysis of those. I will also add some comments regarding usability resulting from our experiences in running this experiment with these various systems, and then finally conclude. Now, the TPC Benchmark DS was developed originally about 2006 in order to test the decision support systems, which was kind of like the buzzword of those days. And it's based on a real-world application. We have a retailer that has basically 3 channels of distribution. First, sales on physical stores, sales via the web, and finally sales via a catalog. And the idea is to be able to generate realistic data in a large scale, and then to answer real-world business questions formalized as queries. Now, the data organization for the data schema in this benchmark adopts a snowflake schema. That is, you have basically a set of core fact tables, the sales tables principally, and then you have associated with them the dimension tables. Again, at a second level, there are other dimension tables, which correspond to, let's say, the items in the catalog, the data about the customers, and so on. It also is equipped with a data generator that will generate data at a large scale and, if desired, in parallel. And finally, the workload, which is characterized by 99 queries of different types, reporting and ad hoc queries, also iterative queries that, in fact, represent a scenario in which a user will issue one query and then subsequently another query based on the results of the first one. And data mining, in this case, it refers to queries that are meant to prepare the data that is going to be fed up into the machine learning algorithms. Now, the TPC Benchmark DS consists of basically 3 tests. First is the test for loading the data. So we generate the data via the TPC toolkit generator, and it will generate raw text files in CSV format. In our case, we will upload these text files into an S3 bucket in Amazon. And then from this raw data in text, we'll generate the table files in the adequate column storage format, for instance, org or C for Presto, and Parquet in the case of Databricks and EMR Spark. Now, once the data is loaded, then we proceed to evaluate the queries into tests. First, the power test, we simply will execute the 99 queries one after the other and measure the execution times. There's an additional step in defining the benchmark, which, however, we will omit in our experiments, which is refreshing the data, which is updating the current database with new data that is incorporated into the system. We will omit in this case, considering that this was defined well for decision support systems of the day. It would interest them to consider an adaptation of this procedure, but for modern cloud-based systems. And finally, we conclude with a throughput test, in which we execute queries concurrently. That is, we take the 99 queries, generate a permutation of them, and each permutation becomes what we call a query stream. And we will execute these query streams in parallel. Concretely, we will execute in our experiments up to 4 streams. That is, there will be up to 4 queries executing concurrently at a given time. In all cases, we are using the 1 terabyte scale factor. Now, in terms of the hardware configuration for our experiments, all experiments were carried out on AWS EC2 machines. Concretely, we chose the i3 2 times large machine type. It's got the characteristic that it incorporates an NVMe SSD, which will be relevant in some contexts. It has about 61 gigabytes of memory and about 8 vCPUs. So it's a medium-sized machine. In all cases, we will use 1 master node and 8 worker nodes. In terms of the software configuration, well, for Databricks, we're using the runtime 5.5. It is not the most recent. Now, there's 6.0 available, but it's still quite recent. It uses Spark 2.43 and Scala 2.11. In the case of EMR, we're using version 5.26, also quite recent, with Spark 2.43 and Presto 0.220. There are some additional configuration parameters required for the systems. For instance, for Spark, EMR Spark and Databricks, we increase the broadcast time node which is due to avoid certain errors that occur when a long-running query has some tags that appear unresponsive, and that triggers failures. We also, for EMR Spark, had to increase the memory allocated to the driver because our benchmarking application required more memory than was originally destinated to the driver by the default configuration. In the case of Presto, well, in some cases the data loading procedure varies. So we have to enable, for instance, dropping tables directly. We also explicitly specify to use the snappy compression algorithm, which is faster. And I have to specify to use the Presto file system to avoid some errors. And very importantly, we have to increase the total memory available for queries, in this case up to 240 gigabytes, which in some cases mitigated some error that appear during execution, but not in all cases, as I will explain briefly. Now, the benchmarking infrastructure is quite simple. We basically took the TPC toolkit, Dockerized it, and this toolkit enables to generate data, the raw text data files, and also the queries. In the case of the data files, we upload them to S3, and from S3, then they will be used to load the tables in the columnar format that is required. The client application was developed in Java, and it includes the SQL files, that is the queries, and the create table statements. And they are all packaged within the jar, so the jar contains the code and the SQL files. Then it is submitted to the platform that is going to evaluate the queries, which can be either a test platform that we developed, but then the cloud-based systems, of course, which depends on the type of system. For instance, it is similar Spark, we can use Spark Submit. On Databricks, we can use jobs. And also on EMR, we can use steps that will execute this jar. The jar, in this case, will create the database in the columnar format, and then evaluate the queries in the power and throughput test. And it requires, of course, a high-compatible metastore. AWS offers Glue. However, Glue has a disadvantage. It does not support, at least at that time, column statistics, so we opted to use MySQL, which is also used by Databricks. So then the benchmark executed, we log, in this case, the execution times, any errors can occur, the execution plans, and so on, and then analyze it via R-Script or simply by Google Spreadsheets. So once we run the experiment on this platform with the configuration I showed earlier, well, we can get directly to the results. Now, in this, what we call the base configuration, based on the, again, hardware configuration that we saw earlier, we see the execution times. The lowest correspond to Databricks, is less than 10 hours, followed with EMR Spark with over 16 hours. EMR Presto took, in this case, over 40 in this default configuration. And we can see how the time is segmented in the various tests. The load test in Lila, then in yellow the power test, and finally the one that takes the longest time, the throughput test. Again, 4 streams at the 1 terabyte scale factor is the one that takes the most time in red. Now, that is the initial result. Now, what can we do in order to improve these execution times? Well, of course, first we can rely on the cost base of the optimizer of each system. So what we need to do is, well, of course, generate the table level and column level statistics from the data, and then the optimizer will use them to generate a more optimal, a highly optimized query evaluation plan. In this case, these statistics refer, for instance, in the case of columns, the minimum and maximum value of an attribute, the fraction of null values for that attribute, and also the number of distinct values. In the case of tables, that is the total number of tuples or the data size. This is an example from Presto. So we employ these table and column statistics, and we obtain the following results. In the case of Databricks, the time drops to about slightly over 8 hours. EMR Spark is a particular case due to the fact that first, the cost-based optimizer is disabled by default, so it will not take advantage of the table and column statistics. Now, if we were to enable this optimizer, it turns to be, at least in my experience, counterproductive with the total execution time of over 27 hours in this case. Of course, we will keep the initial result because that is the default of the system. In the case of EMR Presto, we obtain a significant speedup, a significant performance gain. Now the execution takes slightly over 24 hours. And we can measure it also alternatively as Speedup. The higher speed corresponds to Presto, although again the total execution time was higher. In the case of Databricks, we obtained about 1.2 in Speedup, and finally on Spark, a slight drop due to the time required for the use of column statistics and that the optimizer is of course disabled. If we were to enable it, we will see a significant performance drop in that case. Again, we keep the default result. Now, in the case of Presto, there were some additional configurations required in order to be able to complete all of the queries, both in the power and the throughput tests. Queries 72 and 95 proved to be particularly problematic. In the case of query 72, we modified it in order to do a manual reordering of the joins, and I'll talk about that in greater detail shortly. In the case of query 95, simply add a distinct clause in order to reduce the size of the intermediate results due to an out-of-memory error. Now, for Presto, we also defined a session configuration that in principle applies to all queries unless it is overridden. First, increase the maximum stage count. That is, there's a particular query that requires about 102. And then provide the optimizer the statistics and then the guiding strategy to define the optimal reordering strategy and also the distribution type of the joins. In some cases, this configuration needs to be overridden. For instance, for particular queries, 5, 75, 78, and 80, we force the use of partitioning joins due to out-of-memory errors at a particular node. Queries 78 and 85, it was better to disable the join reordering via optimizer because it was turned to be counterproductive. In the case of query 67, that was a little more tricky. Increasing the concurrency, we were able to complete the query. My guess is that could be that this manner is it is easier for the system to manage memory adequately. And finally, query 18 eliminated the cross join because the intermediate size results was too large and led to errors. Now, in the particular case of query 72, we take the original order of the tables as is provided by the query. We read it from left to right, left associated. And the problem with this original join order is that it generates very large intermediate results. So one way to reduce the size of these intermediate results is to reorder the joins, moving in this case in blue the dimension tables earlier into the join process, and then we obtain this modified order that in this case succeeds in all systems. Now, what happens when we supply this modified query in this case to Databricks when there are no statistics available? Well, then they would keep the same join order, but they'll do, of course, the pushing down of selection and projections that is expected from an optimizer. However, if the optimizer has statistics, table and column statistics available, it generates an alternative execution plan. In this case, it's a bushy plan with two main branches, we can see. And this query plan is much more efficient. First, it can be evaluated in parallel, and also it generates intermediate tables of a lesser size. So this plan is significantly more efficient. Also, you push down selections and projections. In the case of EMR Spark, then it depends whether the optimizer is enabled or disabled. In both cases, the join order remains the same as the original in the modified query, but the physical plans are different. And in this case, the plan from the enabled optimizer is less efficient. So I guess it's being counterproductive. An additional task we can do in order to increase the performance of the systems, use data partitioning. In this case, we take the data from a table. We only apply this to the largest tables, the 7 largest tables in the benchmark. It doesn't make sense to use them for small tables. And in this case, we will split based on the value of a particular column. In all cases, we use the surrogate keys for the dates. So in this manner, when we create the columnar format data files, they will contain, again, they are stored in S3, one folder for each value of that attribute in particular, as we can see in this screenshot. Now, if we apply this data partitioning scheme, then we obtain the following results. In the case of Databricks, we obtain better performance, slightly over 6 hours. Then for EMR Spark, the time drops to about 9 hours, less than 9 hours, which is quite better. In the case of Presto, well, you can see, well, first it's higher than the original 24 hours we worked on previously, and there were some additional issues. First, to load the largest table, the store sales table, we obtain memory errors. So we opted instead to load the data with Hive. In this case, on EMR, it would run via test. And in this case, we were able to load the data, but in this case, there was some queries that failed, particularly 2 in the power test and 6 on the throughput test. So in this case, the results are not fully valid due to the presence of these errors. Now we can measure then the speedup using both data partition and statistics. The case of the high speedup corresponds to Spark. Again, the total execution time is higher, but its speedup is about 1.8. In Databricks, about 1.6 in speedup. And finally, on Presto, and again, we not fully valid due to the presence of the previous errors. Now we can summarize then all the results. We have them here. The lowest overall execution time corresponds to Databricks using partitioning and statistics. Then with EMR Spark, we also obtain good results. In particular, again, the lowest time corresponds to using partitioning. In this case, like less than 9 hours. And again, in the middle, you can see for Presto in green, we obtain higher values. In this case, the best we obtain in this case is using only statistics, about 24 hours. Now that are the total execution times. TPC-DS defines a score, a benchmark score, which relies on the previous measurements of execution time. And I will not delve into the details of the formula used to compute this benchmark metric. But if we apply to the previous results, we obtain these scores. In this case, a higher value is better. You can see the overall best results is using Databricks with partitioning and statistics. We obtain lower but still good scores with EMR Spark. In this case, the lowest score corresponds to Presto, using, in this case, the best results, again, using statistics. Now, of course, it's important to also take into consideration not only what are the total execution times, but of course, what is the cost associated with running these benchmarks, which of course correspond ultimately in the real world to our actual workload. So we have to calculate the costs. In this case, we opt for a simplified model. We are not considering, for instance, the storage costs on S3. So we consider all the cluster costs. We need to compute them then via the number of nodes. Again, 8 work nodes and 1 master node. The total cost of operating that node per hour, which depends on 2 factors I will explain shortly. And then the execution time in hours to the corresponding benchmark result. Now for the cluster nodes costs, then we divide them into the hardware and the software costs, as the different providers do. The hardware costs are essentially the same for all systems because, again, we use the AWS EC2 i3 2 times large instance. In the case of EMR, the software cost is the same for Presto or for Spark, given to, of course, you can choose to use either system. In the case of Databricks, it's $0.3 in this case for this type of node. Now with these costs, again, it's slightly simplified model, we obtain the results in terms of monetary costs. In the case of Databricks, we obtain the lowest cost overall, $51, using partitioning and statistics. In the case of EMR Spark, we also obtain reasonably good overall costs. In this case, the lowest corresponds to using partitioning. In this case, it was $63. In the middle in green, in Presto, the best result is, in this case, 173 with using statistics. In this case, it's of course due to the longer execution times. So based on, again, now we know the cost, we also know the performance as measured by the benchmark metric. We then can derive a price performance metric. In this case, a lower value is better, since it basically tells us how much money we need to invest in order to obtain a certain performance. The lowest value in this case corresponds to the Databricks using partition and statistics. There are also good results for EMR Spark, the second lowest. And then finally, for Presto, they are, in this case, significantly higher. Now, how can we explain in some level of detail these results? Well, first, Databricks has an interesting feature that is the use of caching. Basically, would automatically cache all the hot data that is being used to process the queries. So this can reduce significantly the amount of data that has to be recorded for the network. In this case, we can see the CloudWatch metrics for a run of the full benchmark with Databricks on the top, and then one with Presto in the bottom. In the case of disk, well, there's significant activity for Databricks due to the fact of the use of the cache. Again, in order to do so, we have to use machines equipped with NVMe SSDs. That's the rationale for using the i3 2 times large machines. In the case of Presto, it's based on mostly in-memory processing, so there is basically no disk activity. Looking at the CPU utilization, in the case of EMR Presto, there are some values that drop a bit the CPU utilization. You can see at the bottom. In this case, what happens is that there's some queries that in particular will appear to lock the resources that cannot then be assigned to other queries that are running concurrently. You can see the bottom corresponds to the master node. And in terms of network traffic, the overall network traffic of the cluster, in the case of Databricks, there's significant traffic, but this is even higher in the case of Presto, due to the fact that first there's no cache, so there's more data that needs to be recovered, and also it depends on the probably more efficient query execution plans for Databricks. Now, I will now add some comments regarding the usability and developer productivity of the systems based on our experiments in running this benchmark. In case of features, they are overall quite similar for different systems. But all of them offer provide the alternative to create clusters via either the GUI in a flexible manner, and also to configure the corresponding system via cluster creation time. That is, you can define which configuration you want to use, and it is applied to the system. Doing so by means of, for instance, an utilization script can be quite tricky, so this is important to have. Also, in some cases, you want to have a distributed file system. That is, you want to save, for instance, in our case, we save the execution times and the execution plans and the results and so on. But then you can save the data or access data from every node in the cluster. In Databricks, you have the DBFS available on the go. In the case of EMR, well, what you can do, and in fact we did, was to mount a volume of EFS, of Amazon EFS, and then you can use, you have a distributed file system at your cluster. However, it takes this additional step. All of them support notebooks, although in the case of EMR, that is done via Zeppelin. And we can say that Databricks has a truly integrated web interface. In the case of EMR, for instance, you want to run either the Presto or the Spark GUI, then you have to create an SSH tunnel, which is one additional step. You have a more integrated interface with Databricks when you have access to jobs and the data catalog and so on. All of them enable JDBC access. It's important in some cases. Then, of course, only the Databricks and the EMR Spark, the Spark-based system, support a programmatic interface via the Scala conventional Spark API. In the case of job creation, well, we mark Databricks as distinguished because it enables to properly create a job that they can specify and access later on the different configurations. In the case of Presto and Spark, however, you can do steps, which is run the full benchmark jar or a Spark submit with the jar to run the entire benchmark. So it acts in a similar manner, but it's not quite the same functionality. Also, fortunately, all of the systems provide a good visualization interface for the query plans. We can see already in this talk, in this conference, examples of the Spark's UI. And also the UI for Presto has been improved significantly in more recent versions. So it's also very useful. And you are interested in monitoring resources, their utilization, well, you can use CloudWatch on Amazon, which of course has some additional cost, or you can also have Ganglia at your disposal. So overall, they all provide very good functionality. Now, to conclude, well, first, in terms of the benchmark results, we can see that Databricks proved to be, in this case, about 4 times faster than EMR Presto. In the case default configuration, not using table and column statistics. If we do apply this table and column statistics, then it's still significantly faster, about 3 times as fast. Now, if we compare it with EMR Spark, then the difference is smaller. Still, Databricks proved to be more cost-effective. And again, why is that? Well, it's first the most efficient runtime that is being developed by Databricks. Also, it has this cache functionality. It will automatically cache that hot data that can significantly speed up queries. And also, it has a significantly more effective cost-based optimizer that will make better use of those table and column statistics to generate more efficient query evaluation plans. Now, also, we can note that both EMR Spark and also Databricks make a better use of data partitioning, obtain in this case significant speedup by our partitioning scheme, and also they deal better with concurrency when we have multiple queries running at the same time. Now, also, we have to note that Presto, EMR Presto, in this case requires some additional tuning, even in some cases at the level of particular queries, either modifying the queries or changing the configuration for that query in particular. But this was minimal for both EMR Spark and also for Databricks. Now, in terms of functionality, well, they are about similar, as I have just covered. However, we can see that Databricks is more user-friendly in some aspects. So in that case, this could be a better option. If you have an heterogeneous team considering people who are data scientists, also data engineers, and so on, it can be more convenient. So finally, of course, I would like to invite you to test the systems by yourself. They are all great systems developed by very knowledgeable people and excellence in their own respects, very true engineering fits of computer science. So finally, I hope that you found this talk helpful. Now, thank you very much for your attention. I wonder if I think we have time for some questions.
Okay. Yeah, we do have 5 minutes.
Thank you for the session. It's so good. I just have one question about Presto. Are you using Starbucks Presto or the Presto?
No, it's the Presto. It's Presto that comes with EMR. You create your cluster on Amazon EMR. Okay. And then it has this version of Presto based on the open source, but I don't know how much
modifications because the Starbucks Presto has another time of CBO, cost-based optimized, and I just don't know if it's the same because I don't know. It's it.
But it's the same. We would like to also maybe in the future consider run experiments with both Starbucks and or alternatives for Presto.
Okay, no problem. Thank you.
Hi, thanks for your presentation. I was wondering, in your benchmarks, were there any queries or cases where Presto outperformed Spark?
Yeah, there were a few, but the difference wasn't that large. So there was a fraction of queries that did run faster on Presto.
Which type of queries?
I didn't categorize it by particular type. They were not long-running queries in that case.
Thank you for your talk. I have one question. I saw you have like a big NVMe disks under the machines.
Yeah.
And they're quite expensive. And in the disk users, we saw like Spark heavily uses these disks. Presto doesn't because there was no activity on the disk. Is it a bit of an unfair comparison because it might be better for Spark to have these disks, but for Presto we might want to add more expensive
Yeah, that is very true. In this case, EMR Presto cannot take advantage of those NVMe SSDs. Where we wanted to test on basically the same configuration, it would necessary to run kind of design an experiment that you basically makes better use of about the same cost in terms of the monetary cost of the cluster, but maybe machines with more memory. Because in this case, I think Presto definitely will benefit more for larger memory than having SSDs. And also the people from Presto that wrote a paper discussing that, and they mentioned that, well, for Facebook, well, they have machines with large amounts of memory, and of course, enormous clusters. So they saw as more cost-effective to rely on those machines with large memories. In this case, the advantage of using a system that employs cache is that, well, those NVMe SSDs are indeed more expensive, but you only use them for the time that the cluster is created in the cloud. So yes, it will require, it was a bit unfair, but we had to keep consistent among the benchmark experiments.
Thanks for your talk, firstly. And secondly, what was the purpose of using org format for Presto and Parquet for anything else? Because as far as I know, Presto also can work with Parquet.
It certainly can work with Parquet, and in fact, initially we ran experiments with Parquet. Then we made comparisons with ORC, and found that org was actually slightly faster. So we decided to keep ORC in this case. I believe, but I'm cannot be entirely sure, that in terms of engineering, the source code base is more solid in using org than using Parquet in the case of Presto. But it will have run as well on Parquet.
I think we have time for one or two more. Anything else? Okay. Thank you, Victor.
Oh, thank
very
you.
good talk.